What is a cancer? The name cancer comes from the Greek word for a crab and refers to the claw like blood vessels extending over the surface. Normally, cells develop independence from the normal signals that control and supply demand. The healing of a wound is a physiological process. The cellular response is coordinated so that proliferation occurs when it is needed and ceases when it is no longer required. The whole process is controlled by a series of signals telling cells when to divide and when not to divide. Cancer cells escape from this normal system of checks and balances. They grow and proliferate in the absence of external stimuli. They proliferate and grow regardless of signals telling them not to. And oncogenes, these are aberrant forms of normal cellular genes. These oncogenes are key factors in this process. According to the scientist Hayflick, normal cells are permitted to undergo only a finite number of divisions. For humans, this number is between 40 and 60. The limitation is imposed by the progressive shortening of the ends of the chromosome called the telomere that occurs each time a cell divides. All the chromosomes undergo this telomeric shortening. Telomeric shortening is like a molecular clock, and when it's time up, the lineage will die out. Cancer cells can use the enzyme telomerase to rebuild the telomere at each cell division. There is no telomeric shortening happening in the cancer cells, and the lineage will never die out, and the cancer cells achieve immortality. Normally, cells that find themselves in the wrong place normally die by a process called apoptosis. Apoptosis is a form of programmed cell death which occurs as the result of internal cellular events instructing the cell to die. This apoptotic process is an important self-regulatory mechanism in growth and development. Cancer cells are able to evade this apoptotic process, which means that the wrong cells can be in the wrong places at the wrong times. A mass of tumor cells in the absence of blood supply cannot grow beyond even 1 mm diameter. This places a severe restriction on the capabilities of the tumor. It cannot grow much larger or spread widely within the body, but the mass of tumor cells are able to attract or construct a blood supply, and it is able to quit its dormant state and behave in a far more aggressive fashion. The ability of a tumor to form these blood vessels is called angiogenic competence, and it is a key feature of malignant transformation. Cancer cells have no respect for the structure of normal tissues. They acquire the ability to breach the basement membrane and gain direct access to the blood vessels and lymphatic vessels. Once the cancer cells gain access to these blood vessels and lymphatic vessels, they have acquired the potential to use the body's natural distribution system. Providing false information is a classic military strategy. Degrading the command and control systems of the enemy is an essential component of modern warfare. Cancer cells almost certainly use similar tactics in their battle for control over their host. The characteristics of the cancer cell arise as a result of mutation. Only very rarely is a single mutation sufficient to cause cancer. Multiple mutations are usually required. Cancer is usually regarded as a clonal disease. Once a cell has arisen with all the mutations necessary to make it fully malignant, it is capable of giving rise to an infinite number of identical cells, each of which is fully malignant. These cells divide, invade, metastasize, and destroy. But then, ultimately, each cell is the direct descendant of that very original primordial transformed cancer cell. A cancer is in a genetic ferment. Cells are dividing without proper checks and balances. Mutations are arising all the time within the tumors, and some of these mutations, particularly those in tumor suppressor genes, have the ability to encourage the development and persistence of further mutations. This gives rise to the phenomena of genomic instability. As it evolves, a cancer contains an increasing variety and number of genetic aberrations. The greater the number of such aberrations, the greater the chance of increasingly deviant behavior and the pace of malignant transformation. Both inheritance and environment are important determinants of cancer development. Neither influence is totally dominant. Using a familiar example, not all smokers develop lung cancer. At the same time, lung cancer can occur in people who have never smoked. The debate concerning the relative importance of the two factors has recently become polarized. Scientists like Tomasity and Vogelstein claiming that cancer is largely a random process, more so of a bad luck. The contrary view expressed by scientists Wu Powers and colleagues is that extrinsic risk factors make a substantial contribution to the development of cancer.